Hello everyone. So today let's discuss the algorithm Euler to technique, right? So previously we had discussed the centroid decomposition. So there are, as I had said earlier, so there are only two algorithms left in the tree-based algorithm, right? So Euler, this is Euler to technique algorithm, right? So let's see what the definition part says here. So the Euler to technique, also known as ETT, is a tree traversal method used to flatten a tree into the array. So again, this is very important. It is a tree traversal method used to flatten a tree into the array, right? Such that each node subtree corresponds to the contiguous segment. This one, what do we call? Each node subtree corresponds to the contiguous segment. It's mainly used in the problems involving subtree queries or lowest common ancestor computations efficiently, right? It's mainly used in the problems involving the subtree queries or lowest common ancestor computations efficiently, right? Let's move on with the explanation part, right? So just listen to this carefully. The same thing will be implementing in the form of code, right? So let's imagine performing a depth first search, DFS, on the tree, right? So when we enter a node, we record it, right? So when we enter the particular node while we're performing the DFS, so we will record that one, right? So when we exit the node after visiting all its children, we record that one again, right? So when we enter the node, then we record it. When we exit that node after visiting all its children, then we record that one again. We know this. So this creates a sequence that represents the entry and exit times or the position of each node, known as the Euler tour of the tree, right? This, what it does, it creates a sequence that represents the entry and exit times of the each node, known as the Euler tour of the tree, right? So for a tree like this, suppose we are considering this tree, right? So we have considered basically this tree, 1, 2, so 3, 4, this one. From 3 we have the node sub. For the 3 we have this one, sub children 5 and 6, right? So the Euler tour traversal order might look like this. So we will be going with a 1. For the 2 it will be 2, again 2. From the 2 it is 3, 2 to 3. Then we have 5. Again we'll be going with a 5 because we have to go to this one, 6 via 3, 5 again. So we'll be making use of the 6. Again we'll be making use of the 6 because we have to move towards the 3. Then the same thing goes for the 4. 4. Finally, 1, we have to move towards the 1, right? So this one, 1, right? So this is Euler to traversal order, right? It looks like this. After we'll be performing DFS for this one, right? So this one, 1, 2. So we have to move to the 3. So again, from the 2 to 3 we are going. Then this one, from 3 we are going to this one, what do we call 5 basically, right? From 3 we are going to 5. So we have to move to 6. So from 5 we have to move 6, right? So we will be going via 3 itself. So for the 6 we'll be going with a from 5 to 6 basically. So this is fine to the 6. So again we have to consider 3, 6. We have to go to the 3. So again we'll be considering via 3 itself. So 663. Again we have to move to the 4. From 3 we have to consider 1. It will be 441 or 414. This is fine, man, right? So 441 finally, right? So I hope this is clear, man, right? So every node appears twice, right, on entry and the exit, on the entry and the exit, right? So that's what I said here. This creates a sequence that represents the entry and exit times or the positions of each node, known as the Euler tour of the tree, right? So we have to first we have entered 2, then we have to move towards the 3, right? So this one. So again we will exit this one 2 and we go to the 1 and we go to 3, right? Entry and exit. So this will be repeated twice. So 3 is also repeated twice, but we have considered here. We have written here, right? So this is fine, man. Every node you can clearly see here. 1 is repeated twice, 2 is repeated twice, 3 is repeated twice, 4 is also repeated twice, 5 is repeated twice, and the 6 is also repeated twice. entry and the exit basically, right? So every node appears twice on entry and the exit. So this what it does, it helps representing a node subtree as a range in this array, enabling range queries like sum, minimum, etc. via the segment tree or the Fenwick tree, right? Yep, this is fine, man. Now let's do one thing. Now let's go with a Euler tool technique, right? This one algorithm. Yep. Let's move forward with the this one. Let's move on with the this one algo basically. Let's try to implement the same thing whatever we have discussed on the this one explanation part. So let's try to implement that one in the form of algorithm. So the first step here would be we have to define the tree using the adjacency list representation, right? So this one tree we are having here basically from one so adjacency list here. So from one, which are the nodes? This one, it is going to two, it is going to three, and it is going to four. So this will be from one. Sorry, what do we call? Yeah, from one it is two, three, as well as four. So we are going with the adjacency list, right? So from two, we are able to go to none actually, right? So we already we have from one to two, right? So from two we have none. So let's represent this one by the empty array. From 3, we are able to go to 5 as well as the 6, right? So from 3, we are able to go to 5 and 6. See here, this one 5 as well as the 6. We have to consider 4, 5 and 6. 4, from 4, we have already considered this one 1 to 4, right? 4, again, none, empty. From 5 also it is empty. We are not able to go. So we are not able to go. So this is fine. 4, 5 and 6, we have to just represent this one in the form of empty array, right? So adjacency list. This is fine. This is how we go with the adjacency list basically. So let me go with a graph here. This one from one, we are going to two, three, as well as the four, right? From two, it is empty. From three, it is five and six. What happened here? So I didn't give comma here. From four, let me give four, five, and six here. Let me give colon thrice. Sorry, colon, colon, colon. So this is five. So these three we have empty that I showed, right? So this is fine. Empty, empty array. So sorry, finally empty. Right. So we have successfully defined the tree using the adjacency list representation, right? So let me come out of this one entirely. Now, after defining the tree using the adjacency list representation, let's move on with the second step. Nothing but we have to initialize the variables, right? First, let's go with the Euler tour. Let's go with the entry time and the exit time. Also, let's go with the time. Euler tour is nothing but it stores the Euler tour sequence, right? So I'll just go with a Euler tour variable name. Let me assign this one to the empty array initially. Then let's go with the entry time here. Mm, sorry, yeah, entry time. Let me initialize this one to the what do we call? Mm, yeah, flag races. This is fine, man. Let's go with the exit time as well, right? So this one will be exit time. Exit time. Let me initialize this one. Oh, sorry. This one I didn't keep equals here. That is the reason it is screaming. This is fine. Yep. Now let me initialize time to 0, right? So this 0, we have initialized this one to the variable time, right? 0. So this is nothing but the global time counter, man. Don't get confused, right? So this is required. Now, as we had discussed earlier, let's define the DFS function. We have to perform the DFS function on the Euler tour, right? So let's define the DFS function for the Euler tour. So I'll just go with the def DFS here, node comma, let me pass parent here. This is fine. Yeah. Let me go with global time. This is fine. Now time equals time plus 1. Also, let me go with the entry time here. entry time of node. This one, let me assign this one to the time. Also, let me go with the Euler tour dot append. So let me give append here of node, right? So this is also fine. So now let's do one thing. Let's traverse all the children. So this one will be for child in graph. So this one graph of node. If child, if it is not equal to parent, this one, hmm, let's call the DFS. Let's recurse here. What are the things that we need to pass here? Child as well as the node, right? So let me pass child as well as the node. Finally, let me go with the Euler tour as well. This one. Yep, we have made use of this one variable name Euler tour. So we have to append the node to it. So let me go with append. Let me pass node within the parenthesis. This is fine. We are just adding the current node again after returning. Nothing but exit, right? After the exit, basically. Now this is fine, man. Let's do one thing. Let me go with time equals time plus 1. Time equals time plus 1 we have to go with, and we have to mark the exit time. So I'll just go with exit time here. Where is exit time? Yep, exit time of node. Let me assign this one to the time. This is fine. Yep. Now the next step would be, or the fourth step would be, we have to start the DFS from the root node 1. So this one will be DFS of 1 comma minus 1. This is fine. Now let's move on with the fifth step. Nothing but we have to print the results, right? Just for the sake of interactiveness. So I'll just go with the print Euler tour sequence. This is fine. And let me pass the Euler tour. Fine. Let me go with a print statement again. So this time let me go with entry times. So this one will be entry times. So this is fine. Yep. Let me pass the entry time over here, man. Let me give entry. Yeah. And finally, let me give print again. We have to mark the exit time as well. So I'll just go with the exit time. Yep. Let me pass exit time here. This one. Right, so we are just printing the this one Euler tour sequence as well as the entry times and the exit time. So this one I'll just give S here entry times and the exit times, right? So this is fine, man. So what is the output that we need to get? We already know this one, right? The sequence I have already shown you. So this one I have already mentioned here. 1, double 2, double 3, double 4, double 5, double 6. Basically, all the nodes has to be repeated. So here it is 1 double 2 3 double 5 double 6 3 double 4 1, right? Entry time, for the entry time 1 is 1, for the 2 it is 2, right? For the 3 it is 4, for the 5 it is 5, for the 6 it is 7, and for the 4 it is 10. Exit time also we will be marking in the similar way, right? So for the 2 it is 3, for the 5 it is 6, for the 6 it is 8, for the 3 it is 9, and 4 it is 11, and 1 it is 12. So let me run this one and then we can discuss the same actually. Let me copy this one entirely. Let me come here, Control J, Python, Control this one, file name.py. So we are getting the entry time correctly. Basically 1 2 1 3 5. So we are not getting the correct output. Just give me a second here. So basically this is also correct one. So this is also one of the valid output. So this we call it as path re-entry in the Euler's traversal tour traversal. Basically, you can just check, you can just Google. So this is called path re-entry, this one Euler to technique traversal, right? So this is also one of the valid this one answers, right? So this is also valid, this one what we have considered, this one this is also valid output. You can just check, right? So this is fine. So entry time and exit time we have already discussed this one. You can just check the same, right? So Euler tour sequence, this one, what it does basically, here we are getting this output, right? So this one, it shows the order in which the nodes were entered and exited, right? So I can just check for the example, this one, what do we call? Note this one here, note to appears twice or note to appears single time as well, right? So this is also one of the valid outputs. You can just check in the same way that I had shown you earlier, right? So entry time, what it does, it marks the timestamp when the DFS first visits each node, and exit times, it marks the timestamp when DFS finishes the processing of the node's subtree. So this is nothing but parent re-entry version of the Euler tour traversal technique. So this is also one of the valid outputs, right? So we can have the multiple outputs here. Don't get confused. This is not wrong. This is also correct, right? So this is fine. So again, for any node V, its subtree corresponds to all the nodes with the entry times in the range entry of V, comma exit of V when it comes to Euler tour technique algorithm, right? So we are done with this algorithm, right? So we are done with this algorithm, right? So next we are left with only one topic in the trees based algorithm, nothing but square root decomposition, right? So nothing but we are left with square root decomposition on the trees, right? So let's finish it off tomorrow, that one. For now, we are done with this part. So let me summarize whatever we have learned so far so that we don't forget things, right? So let's discuss some of the very important points that we need to remember. So now, first thing here would be, so Euler 2 technique, also known as this one, ETT, we call this one ETT, right? So ETT converts the tree into the linear structure when maintaining the subtree relationships, while maintaining the subtree relationship. Sorry. Yeah. The second point here would be, so for each node has this one, what do we call? Entry time of V, this one, when the DFS enters, when the DFS enters, right? So when DFS, this is F, not E, when DFS entry time, and it has the exit time as well, right? So it has the exit time of V as well when the DFS leaves, right? When the DFS leaves. Again, let me tell you the first 2 points again. Euler 2 technique converts the tree into the linear structure, nothing but the array, while maintaining the subtree relationship, right? The second one, each node has entry time of V and the exit time of V when DFS enters and when the DFS leaves, right? So subtree queries become the range queries. Now subtree queries, this one becomes range queries, right? So it becomes the range queries, right? So the final point here would be, so it is commonly used in LCA, nothing but the lowest common ancestor problems. It can be used in the subtree sum or the count queries, right? Subtree sum or the count queries as well. The final one, it can be used in the dynamic trees using segment trees, dynamic trees using segment trees, or this one, Fenwick trees, or BIT basically, right? Or BIT, right? So these are some of the very important points that we need to remember, right? So we are done with this algo. Next, as I've said, we'll be going with the square root decomposition on the trees. For now, this is it. Thanks for watching, guys.